So the last time that we talked about this result right here, so if you have an extension f of k that is finite dimensional, or degree of the extension is finite, then f is both finitely generated over k, and in fact it's algebraic. So any small extension is algebraic. I pointed out last time that this is not a necessary condition. You can be very large and still algebraic. So let's go through this. Let's tackle algebraic first. So suppose U is some element of suppose U is an element of F, just any element of F, and suppose 3 of F over K is precisely N. Now let me make the observation first that degree of F over K, KU is an intermediate extension, so we've got this going on. And since this is N, the extension KU over K is no more than N, right? But you don't expect it to be less. So the set of elements U of those 1 U squared plus UN is linearly. Right? Because there's in fact N plus 1 elements in here, so they have to be linearly independent. So there exists K0, K1, Kn, K, not all 0, such that Kn UN plus K1U plus K0 0. Yes. Yes. And I also meant that to be a big. So you okay. So that gets us the first result, right? And of course, it's important that not all the K's are 0 here, otherwise that could be 0 polynomial, which would be exactly the proof. Also, since the degree of F over K is N, that means that F is a n-dimensional vector space of K. So basis say A1, A2, AN for F over K. So in particular, any element of F is a K-linear combination. So of course, all these elements are by definition in F because they're vector space basis. So K and all these things are in F. This containment is obvious. And the other containment is because you don't even really need products of these. All you need is K-linear combinations. Okay. Any questions on that? Here is a big one that we needed this previous result for. And this is one of the most important things about the algebraic property, and that is its transitive theory. A1. Suppose if F is algebraic over E and E is algebraic over K, then F is algebraic over. Okay. So we're going to kind of bootstrap the previous ideas. Let's suppose we have U and F. To show that F is algebraic over K, really what I need to do is show, just pick an arbitrary element. I need to show that it's algebraic. Okay. Now, getting a polynomial, as I alluded to before, is difficult, right? It's not impossible to do. And I'll give you an example. Anyway, so let's let U be an F. We know that U is algebraic over E. All right. So in particular, we have is a root of E n U n plus E n minus 1 U n minus 1 E1 U plus E0. Well, let me say U. It satisfies this relation with EI and EN non-zero. Again, I want this to be not the zero polynomial, and I might as well take EN to be not zero, because otherwise, why would I have started it there? Now, the question becomes, how do I get this all the way down to K, right? Because now, what have I done? I've shown that U is algebraic over E, so I'll get these coefficients of E. And I know that each one of these coefficients is algebraic over K, but making that step, that's difficult, right? Here's the observation. Previous equation. So we'll take a minimalistic approach, like Richard Gere's active, right? What's the smallest amount that we need here? The previous equation shows that U is actually algebraic over E0 up to E. That makes it a little bit better, right, at this observation, because really, all we really need, is we don't need all of E for you to be algebraic, we only need these coefficients. Now consider the tower fields. Right. K inside of K E0, out of K E0 E1 inside K E0 E1 En K E0 E1 En. So this jump, right, is fine. Because E0 is algebraic over K, right? Right here. The next jump is fine too. As E1 is algebraic over K0. In fact, I don't even need K0. It's actually algebraic over K, so it's algebraic over the larger extension, right? So the degree of K E0, oh, my notation back. I should reverse these. Yeah, I've got the big field and the small field to turn around. I apologize for that. Just swap these out. K E0, E1, En, U over K is equal to whatever that product is. M0, M1, M and plus. It's fine. So every element algebraic over K. U So F is algebraic. Because we've shown that an arbitrary element in F is algebraic. And here we did this with field extensions and things like degree using the previous theorem. We never used polynomials, so let me give you kind of a simple example here. This is sort of an example why this proof is the way to go and this is the best way. Here's the question. Minimal polynomial. Uh, some polynomial right field. Now we're and let's face it, as far as minimal polynomials go, radicals can be radical through. Piece of x and 4 minus 10x squared plus 1, maybe. Let's find out, Charlie. Square that. Well, it's going to be 5 plus 2 radical 6. Great. Now, I noticed something here, so let me be lazy and skip a step because I see something here. What happens when I square that? I get 25 and 24 is 49 plus 20 radical 6. Everybody agree with that? And the key ones with this and this, because it only involves radical 6. And so if I'm clever, I can just use one of your algebra for this. So I have x4 minus 10x squared. That's going to kill the radical 6 part. Everybody agree with that? And what's it going to leave me with? It's going to be 49 minus 50 is negative 1. So I got to have a plus no factor. But it's not at all obvious that's what the minimal polynomial is going to be. Test it by the quadratic formula. You can apply it twice, and you should get 4 roots plus or minus radical 3 and plus or minus radical 2. If you're super clever, you might have done this by conjugating various things. Multiply this by radical 2 minus radical 3 and various things like that. We'll see that more here. But the point to this is, when I have 2 elements that both have some minimal polynomial that's even pretty reasonable, where in the world is that? And you would probably guess that I don't have to work very hard to come up with examples that are much, much more intractable than this one. Here's the corollary. And this is an incredibly important one. This is a big one. Let alpha and beta be algebraic, okay? Uh, and so are alpha, beta, uh, alpha plus, actually, let me do something even more. K1 alpha plus K2 beta, K1, 2, and K. So in particular, you take these both to be 1, alpha plus beta is there. Alpha beta, alpha over beta with beta 0. So in other words, sums, products, and quotients, as long as you're not dividing by 0, are all algebraic over K. In particular, if K is taken F, then alpha F such that alpha is algebraic over K is a subset of F. So in other words, if you have an extension, any field F that contains K, instead of everything in that field is algebraic over K, is a subfield. So let me prove corollary. Consider this is you now know K alpha beta is algebraic. Because this is an algebraic extension, and of course beta is algebraic over K, so it's algebraic over this intermediate field as well. And K1 alpha plus K2 beta, alpha beta, and alpha over beta, if beta is not 0, are even. So in particular, they're algebraic. Any questions? Okay. Let's start. So a couple of sections, fundamental theorem of Galois theory. I've got to tell you, I've got to give you a little setup here. So, I'm gonna tell you a little bit about this. Some background definitions, and I'm gonna do an example that, although reasonably small, gives a pretty wide picture of, if you understand the example I'm gonna give you, it goes a long way to understanding what happens. I'm gonna refer back to this example as we go through the proof, which will take us a little while to do. Let E and F be field extension K. These two field extensions we will call sigma a K homomorphism. Is K homomorphism. If sigma is a K module homomorphism and a field homomorphism. So just as it stands, it's a field homomorphism, and it behaves like an R-module homomorphism as well. That is to say, you can pull out factors of K. The group of all K homomorphisms, K automorphisms. Yeah. So what I mean here, so this is a K homomorphism. And isomorphism. So you can factor K's out of the homomorphism, and it's also an isomorphism from F to itself. It's called the Galois group. And it's denoted as a number where if you see it, we call it lazy people like this. Notice this is a group because these are all automorphisms. So the inverse is defined. It's also an automorphism. And notice that by the definition, notice that a K homomorphism must fix all of K. It's going to be very, it's like the first result, but it's going to be very important. It comes up time and time again. Top position. Let's let F be an extension of K and sigma the Galois group. By the way, the Galois group is not empty because the identity function is always there. Identity function on F, that certainly fixes K as well. If U in F is algebraic, And we have minimal polynomial. Okay, well, we got that. And g of x and k of x is such that g of u equals 0, then sigma is a root of g of x for all sigma. Sigma u is also a root. So sigma is g of u, apply sigma. Why can I do this? Because all the coefficients of G are in K, so I can pull them out. So more explicitly, so this computation, of course, shows that sigma u is root of G. If G of X is K0 plus K1 X plus Kn Xn, then G of U is K0 plus K1U plus KNUN. And so sigma of G of U is sigma of this mess. And I can basically factor all this stuff out. U plus KNUN K0 plus K1 U C plus KN. Exactly what we want. So if you have an automorphism of F that fixes K, then any root of a polynomial is taken to another root by an element, one of these sigmas. Here's an example. Here's these. Let that be a free integer. Consider F U radical. So D might be 2 or a prime or something like 6. It's just got to be divisible by no square other than 1. Anybody want to venture a guess as to what the Galois group is over Q? So a typical element is looks like A plus B radical B. And we know that you must take, so here's what I'm, this is A plus B sigma radical B. It has, this is not one, two rational numbers. Rational numbers that are fixed. Where can D go? Or where can radical D go? What's the minimal polynomial radical D? What's that? Radical D and minus radical D. There's only two places this can go. And that, of course, would be the identity on the models. Do you remember back when you were in high school and your teacher would give you something like fraction 1/1 plus the square root of 2 and say, rationalize the denominator? I remember that. What your teacher didn't tell you is multiply that element by its Galois conjugate for the obvious reasons, perhaps. But that's what's going on. The Galois group here. Notice when you apply this conjugation, automorphism twice, you get the identity. Right. Let me give you an example here. This is the one that I think we should talk about this today. It's quite believe it's tomorrow. Right, 2, 3. I'll now do the real root x cubed minus 2. Let omega equal minus 1 with radical minus 3 over 2. Here you can see it come up. Let me point out that omega squared and omega bar are the same thing. They're equal to minus omega minus 1. These identities are all very easy to even derive by hand. Now, when we look at this field here, it turns out you can verify this, but let's let F, the smallest field that contains alpha, the cube root of 2, and this crazy cube root of -1. This is the smallest field where x squared, x cubed minus 2 has all there's the three roots of x cubed minus 2. It's alpha, alpha omega, and alpha omega bar. So that's the smallest field where you've got all the roots. A basis. So you can verify this. It's not terribly hard to justify this. A basis of f over q is given by 1 alpha alpha squared omega alpha omega alpha omega. Everything in here in this field is linear complex, including, you might say, well, where does omega bar come from? Notice you add this and this and take its negative sign, you get the omega bar, right? You might say, where does alpha times omega bar come from? You can do play similar games and that. So, what are the possible automorphisms of that? And I want to kind of describe how they might work on the basis. So let me, I'm going to make this large. The original basis one alpha squared, omega alpha squared. I want to look at the possible effect of automorphisms on these 6 basis elements here. And one of them, by the way, is easy. The first thing I'm going to do is I'm going to list the roots. So to aid my computation, I'm going to list the roots of this irreducible polynomial. The roots of x cubed minus 2 look like alpha omega bar. I agree with that. Those are the 3 roots. And I'm going to call this 1. And I'm going to list this so that I can see what happens. Because my previous theorem tells me any automorphism in this field has to take one of these roots to another one. So it induces a permutation on these 3 roots, right? All right, well, let me start here with it. Easy. Oh, okay. I know what this does. Let's see what happens. What happens if we swap? Is it possible to have is there permutation that swaps roots 2 and 3? I bet there's an easy familiar automorphism in this field. You might think of this swap. Complex conjugation. This field contains stuff that's not real. Complex conjugation should be not. So what should complex conjugation do to these bases? Well, I know what it does to 1. I know what it does to alpha squared, because these are all real numbers. The complex conjugation doesn't affect that. But it should take omega to omega bar, this to omega bar alpha, and this to omega bar alpha squared. It should do that. And these, of course, this is because my automorphism takes omega to omega bar and leaves alpha alone. Okay. Can I do, for example, can I swap up first 2 roots? And leave this one alone, right? Let's see what would have to happen here. Alpha goes to alpha omega, and alpha omega goes to alpha. Right? So let's get started on this and see if this can happen. Alpha goes to alpha omega, and omega alpha goes to alpha. So we've got to have that. Right? How about omega? And how can we figure it out? If alpha goes to alpha omega, and alpha omega goes to alpha, then omega is the quotient of these, right? So the image of omega should be the quotient of these. So it should take omega to 1 over omega, which is omega bar. So, and once you've got that, then you know where everything else goes. Where should alpha squared go? Well, if alpha goes to alpha omega, then the square of that should go to alpha squared omega squared, which is omega bar. Right? And now we can put the pieces together. This goes to omega bar, omega alpha goes to alpha. So let's see, omega, let's put it together, make it make sense. Omega alpha squared, 2 omega bars, omega, like that. Let's try one more. We'll go over this more tomorrow. Or whenever we do it. Right. This time we want alpha to go to alpha omega go to alpha omega bar, and alpha omega bar goes to the alpha. Cannot be. Well, let's see. Well, one better than one. Alpha went to what? Alpha omega. Well, this tells me where alpha squared should go, because that should go to alpha squared omega squared. So this should be alpha squared omega bar. Where does omega go in this case? I think omega bar is fixed because the quotient of this should go to the quotient of this. So omega, using automorphism property, should go to omega bar over omega, which is omega bar, which is omega. So it looks like they're fixed here. And from here on out, we should be done. Where does alpha omega go? Well, alpha goes here, and omega goes here. So omega alpha should go to alpha omega bar. And what about this last one? Well, alpha squared goes to this, and omega goes to itself. So this should go to okay. Any questions on that? Notice that these permutations so far all do the same thing, or all do something different, right? Here's the identity. The identity is different from this. Let's see, the only one that this could be the same with is this, but then they differ here. So notice that I have 4 so far. Everybody agree with that? 4 automorphisms so far. It seems to do different things. How many should there be then? There should be full 6, right? Because you're not going to be able to stop at 4. Think about why you can't. Or 5. So there have to be 6 different automorphisms. And that's the most possible, right? Because there's only so many ways, 6 in this case, to commute the 3 roots of the polynomials. So we'll go through this table a little bit more. Try to fill in the other blanks. There's 2 others that I left out, one of order 2 and one of order 3. We'll get to that next time, and we'll talk about some of the stuff that's going on here, because in this table is basically a big chunk of the fundamental theorem of Galois. Any questions? All right, we will see you folks next time.